the function has negative slope. So if this is the tangent, then f primed at x star has negative slope. And what we know is that if the slope is between 0 and minus 1, then we'll get a stable situation. Or if the slope, like over here, or if the slope is much steeper, so that if this curve actually comes down to look like this, if it's very steep over here, then that won't be stable. And so that explains the different behaviors you get. And so because of all this, there's a theorem that tells you about whether a model is stable or not. So for example, let's consider in this case, let's go back to the logistic equation. And it says that xn plus 1 equals fxn has an equilibrium at x equal to x star, and its derivative exists and is equal to r. So you can show in the logistic equation that the derivative is equal to r. Then x star is stable if the absolute value of r is less than 1, and unstable if the absolute value of r is greater than 1. So we get these four cases. If the absolute value of the slope is less than 1, then we get either this case or this case. In this case, the slope is negative, but its absolute value is less than 1. In this case, you go asymptotically to the origin, but you don't oscillate. In this case, you go asymptotically to the origin, but you jump back and forth. If the absolute value is greater than 1, so you've either got this case, or here you've got a negative slope, but its absolute value is greater than 1, then in this case, you just move out from it. In this case, you'll move out, but you'll jump on either side. So if the slope is negative, which is this case and this case, you jump. If the slope is positive, then you don't jump on either side. You don't oscillate. If the slope, the absolute value of the slope is less than 1, so you're between 0 and 1, or between 0 and minus 1, then you're going to be stable. And if the absolute value of the derivative or the slope is greater than 1, then you're going to be unstable. Does everybody understand that? Yeah.
So those graphs, how do you
Which ones? No, this is not going towards the equilibrium. You're starting out here, you're going to the function, then you're going to the 45, then you're going to the function, then you're going to the 45. So you're moving out all the time. In the top one, you go to your function, then to the 45, to your function, then to the 45, and then you see that you go in. Yeah?
So are those graphs only the ones on the top, or the top ones?
Yeah, the top ones are stable, the bottom ones are unstable, the right-hand side oscillate, the left-hand side don't. So when you simulate the behavior for different values of r, as you change r, you're actually working with this case. So this case is the so-called linear case, and it's around the origin. This case, in this particular function over here, you've actually got three equilibria. You've got one over there, and one over there. So you've got to look at the slope over here, and you've got to look at the slope over there, and then you've got to look at the slope over here. Here the slope is negative, here the slope is positive and greater than 1, here the slope is positive and less than 1. So this is stable, this is unstable, and here you can't tell what's going on unless you know what the slope is. And because the slope looks like it's between, in absolute value, it looks like it's less than 1, then this winds in. However, if this was steeper over there, it would wind out. So you're going to see these behaviors, but this is how you get a qualitative understanding of these behaviors. And so you can go through this example, which is a logistic equation, and you can solve for the equilibrium, and then you can show that for this particular equation here, that in order for it to be stable, we require that this parameter r over here lies between 2 and 0. Now, I'm not going to go through this with you because you can go through it yourself. This is the example in the homework that we have, which is this particular model. And Bellows applied this model to populations of several different populations of insects. And again, you can analyze this model, and you can go through this analysis, and you can take the derivative. And you can see that for certain values of the parameters in the model, and in this case you have two parameters. You have a parameter r, and you have a parameter b. Can you read that? You have two parameters, r and b. And depending on the values of r and b, so the shape of the curve will determine how the function goes through this point, which is the equilibrium. When it goes through the point, does it have slope positive or negative? And if it's negative, does it have slope less than, in absolute value, less than or greater than 1? And from that, you'll get the different behaviors. And for some sets of parameters where the value, where the slope is steep here, and so the absolute value is greater than 1, then you'll get this kind of behavior where the population bounces up and down. And so then you can understand how this behavior arises from the dynamics of the population. Okay? So here we come to what's called a bifurcation diagram. And this bifurcation diagram applies to the logistic map. So we can actually go to this Wikipedia site. And this bifurcation diagram applies to this model over here, which is the logistic map. So it's different from the one we were talking about. This is xn plus 1 is equal to r times xn, 1 minus xn, and it doesn't have the extra xn term that the other logistic equation does. Now, you can say, how does this behave for different values of r? And this map tells you how it behaves for different values of r. And I'm going to explain to you what this map tells you. So let's choose a value for r. If you choose a value for r that is relatively small, and that is below the number 3, then this tells you what your equilibrium is going to be. If r is equal to 2.4, the equilibrium value will just be under 0.6, and the system will be stable, and it'll go to this equilibrium value. Once you hit this point over here, this value of r, and you move beyond it, you no longer go to a single equilibrium value, but you oscillate. You go to oscillating between two values. So once you get to a value of r somewhere in here, then what's happening is your solution is behaving like this solution over here. It's bouncing between two values. Everybody understand that? So you bounce between two values. Now you start increasing the value of r. So we increase the value of r to a value that is somewhere in this range over here, and you see that you bounce between four values. You've got a top value and a bottom value, and so you go from there to there to there to there, and then back to there. And so when you simulate that map, and you choose r equal to 3.48, for example, you'll see you'll get 4 values. And so your solution will keep repeating itself. Initially, it doesn't do this because you start off at some point and you have to approach the asymptotic behavior. But the asymptotic behavior here is called a 4-cycle. So what happens when you get into this region over here? How many values do you have? You have 2 values there, 2 values there, 2 values there, 2 values there, 2 values there. So somewhere in the neighborhood of r equal to 3.7, it'll ultimately be oscillating with a pattern of 8 values. Then what happens is that you hit a threshold, and all of a sudden, these regions where you get the whole gray areas, you're just picking up lots of different values. And that's where you get chaotic behavior. But there's a very strange thing about this pattern, is that eventually when you go beyond a certain point, like when you get to this point over here, can everybody see my cursor? There's like this clear region, and what you're picking up is 3 values. You're picking up a value there, a value there, a value there. And a small perturbation, you pick up 6 values. And then you pick up 12 values. So you get this period doubling. You go from 1 to 2 to 4 to 8 to 16. And the interval gets smaller and smaller, and you keep doubling up until finally you hit a threshold, and it's like your period went to infinity, and now you're in chaos. Then you keep going, and you get to a point where there's like a 3-cycle, and then a 6-cycle, and then a 12-cycle. So it's also period doubling, but from 3. And then in between these, you get these chaotic behavior regions. Now, if you look at this point over here, this thing looks exactly like this whole thing in miniature. So it's called a fractile pattern. And fractile patterns are really amazing. Now, I'm going to tell you about fractile patterns, but before we talk about fractile patterns and these incredible mathematical structures that can arise, we have to talk about equations that are higher dimension than 1 dimension. And so we're going to get into 2-dimensional systems of equations. So far we've been talking about models where we can write down the model in terms of one variable x, and its value, let's say I'm going to go to t plus 1, is some function of x at t. So that tells me how a single population grows. But now what happens if we have 2 populations that depend on one another? Then we might say, okay, we have another population y, and we say y at t plus 1 is equal to g of y at t. So these are 2 separate populations, they're not interacting. But what happens if they interact? So that the rate of change of x depends not only on the value of x, but also on the value of y. And the rate of change of y depends not only on the value of y, but also on the value of x. Then we can write down a 2-dimensional system like this. So can you think of any population processes where there are going to be 2 populations that depend on one another for how they're going to change from one time period to another? Yeah? Predator prey, okay. You want to give a more specific example, or somebody does? Yeah? Yeah, boom and bust arises, but give it a specific example, yeah? Yeah, so they're classic examples like foxes and hares. We're interested in agriculture, in biological control. So we're interested, for example, in ladybird beetles and aphids. So ladybird beetles eat aphids, and aphids eat your plants. But if we're just interested in the aphid population, we see that the aphid population is growing. We release some ladybird beetles, and the population of aphids can't grow as fast because the ladybirds come in and eat them. So depending on how many ladybird beetles are around will depend on how many aphids you have in the next generation. If there are lots of ladybird beetles around, you'll have fewer aphids because a lot of them will be eaten. On the other hand, from the ladybird beetles' point of view, the more aphids there are, the more food there is for them. So their growth will depend on the number of aphids. So you get models like this where it depends on 2 parameters. You also get models like this. X at t plus 1 is some function of x at t and x at t minus 1. So what's happening in the population depends not only on how many individuals there are at this time, but also how many individuals there were at the previous time. So there's a famous mathematician, Fibonacci, who lived in the 14th century, and he posed this problem with rabbits. And he said, okay, suppose you initially have a pair of newborn rabbits. You let these rabbits age a month, and then a month later they give rise to 2 new rabbits. So you're saying a newborn rabbit has to wait a month, and then a month later it can reproduce. Now, of course, this is some kind of idealized rabbit. And these rabbits live forever, they don't die. So we've got these rabbits that start out, they live for a month, then they reproduce. So there they are, and they're young. They're young, don't reproduce yet, they live for a month, but these move on to then reproduce again and make new rabbits. And so now what you have is the original pair, the new young from the original pair, and then the first generation getting a month older. Now, the generation that got a month older, now they're ready to reproduce themselves and go forward. These individuals go forward and they reproduce again, and these individuals go forward. And so you go on like this. And so how many rabbits do you have after 10 generations? So Fibonacci said you can show that the number of rabbits in any month is equal to the number that were there in the previous month plus the number that were there the month before. So explain why this is true. So you can go through and you can convince yourself that this sequence of events can be generalized and stated in the simple mathematical formula. Okay? So you can try and work through that. Now you can say the growth rate of the colony during the n plus 1th month is going to depend on how many there are in the current month versus how many there were the previous month. So for example, if we had 100 the previous month and now we have 130 this month, then that's a 30% growth rate. So you look at that ratio. Then from this particular relationship, you can show that this statement here, together with this relationship over here, leads to an equation, a difference equation in R, the ratio each month. And that equation says that R n plus 1 is equal to 1 plus 1 over R to the n. And if you can't work that out, there's the example worked out in the textbook. So now the interesting thing about a model like this is that it's a two-dimensional model in that it has two arguments. Can it be written in a form like this? So if we say let y at time t equals x at time t minus 1, if we do that, then we'll say this is the same as saying y at time t plus 1 is equal to x at time t. Okay, because we just move forward one in time. Now here we have x at time t plus 1 is equal to a function of x at time t and y at time t minus 1, sorry, x at time t minus 1, which we can just write as y of t. So in other words, this equation is just a special case of this equation. So a two-dimensional system like this is a special case of a two-dimensional system like this, where one of the equations has a rather simple form, okay? And what we're going to do is, next week, we're going to study some models like this that have application in biological control. So we're going to look at this whole problem of biological control and pest management using natural enemies. But what I would like to do is I would like to talk about something called the Mandelbrot set. Now the Mandelbrot set is, I'm going to write down this equation. Here's an equation that says x at t plus 1 is equal to x squared at t minus y squared at t plus some constant, which I'm just going to call C1. And I'm going to write down y at t plus 1 is equal to 2x of t, y of t, plus some other constant, C2. So this is a special case of this equation where the function of x and y is given by x squared minus y squared plus c. And g of x and y is given by 2xy plus some constant c, okay? What do you think of this equation? Pretty boring equation. Anybody thinks that this is a spectacular equation? Or is it the most boring piece of mathematics you've ever seen in your life? What is it? Who thinks it's spectacular? Okay, GSIs don't count. Who thinks it's pretty boring? Never seen anything like it, don't know what it means. Go on. First time you see it. Like, what is it? It's nothing. Just a little bit of algebra, an x and y. Doesn't say anything. This equation, with a few simple rules about how solutions approach its equilibria, or don't approach its equilibria, for different values of C1 and C2, is the most spectacular thing you've ever seen in your whole life. Who thinks I'm exaggerating? You all do. Now, come on, you do. Okay. Who's heard of the Mandelbrot set? Okay, so you know what's going on then. But those of you who haven't don't know what's going on, so I'll have to reveal this to you. Okay, so let's go to the Mandelbrot set here. Okay. This Mandelbrot set looks like this object. This object contains all the points where if you start out, well, let's see, I've got the rules here for the Mandelbrot set. Where is it? Yeah. By varying the value of C, find those values for which the solutions remain bounded. So that is, the solutions don't grow to infinity. All the values of C, of C1 and C2, so if you're looking here, you've got a C1 and a C2 axis, lie inside the set, which has got this potato-like behavior, potato-like look. Now we can hopefully, there's some cases where you can, so what you can show, and it's not being shown here, is that this little knobble sitting on the whole thing is a perfect copy of the whole of this knobble over here. And this knobble has a knobble over there, and also has one over there that's a perfect copy of the whole. So as you go in and you look at these things and you scale them up, you get these replicated copies, and it's the most amazing thing. You can also create other sets from this equation by doing the following. Where is it? By allowing the initial values of this equation to vary, then for given values of C and all initial values, you ask which solutions are unstable. And when you do that, you get the so-called Julia sets, and then you color them in. So let's go back to that. Well, here's the details of the Mandelbrot set. So all these pictures are created by coloring in these different elements in the Mandelbrot set, different colors based